All right, so we will study the subject of optics. We'll study a little physics because we'll be using this when we understand vision. Okay, what is the idea of vision? Again, when you see something, you want to form the image of that object on your retina, which excites the optic nerve, and the brain interprets that as whatever you're seeing. Okay. All right. You guys all know that Thomas Edison was a great inventor, and when he was working on the light bulb, he failed many times. He says, "I have not failed. I've found 10,000 ways that don't work." Yeah. So, okay, so in everything we see that light travels in a straight line. Okay, and that's how our brain is hardwired to think. Okay, so here's a light ray coming from the sun. Here's a light ray reflected from the lake. Okay. So we are going to study the rules of geometric optics. Okay. Look at this. Okay, so okay, so we're going to shine a beam of light. Okay, so this first material is air. This is water or whatever. It's water. So I'm going to shine a beam of light. So you see this beam of light. Now this didn't travel straight line. This beam of light bent when it went into water. And this beam of light, part of the energy was reflected, part was refracted. Okay, when light travels from one medium to another, if the speed changes in this medium, it'll bend. If it travels slower in this medium, the light will bend towards the normal. If it travels faster in this medium, it'll bend away from the normal. Okay, so that's the property. So for instance, oops, I guess I can't, okay. So for instance here, we can shine a beam of light from glass into water. Light travels faster in water than in glass, and it's bending away from the normal. Okay. Here in this medium, light is traveling faster. In this medium, it's traveling slower, and so it bends towards the normal. Okay. So that's called refraction. And you can have two different media. If light travels at the same speed, it'll just go straight. Okay. All right, so that's refraction. Okay, so you can see that here, light traveling from air to glass bends towards the normal. Now, slower it's traveling in this medium, more it will bend. Okay, and the more light bends, again, the slower it's traveling. So the speed of light in this medium is measured by something called refractive index. So if you wear glasses and you go to an ophthalmologist or an optometrist and you get high refractive index glass, light is bending more, and you have to use less material to get the light to bend more. Okay. Okay. Here's a reflecting surface. You see a beam of light is reflected, and and here's a rough surface, and light is diffusely scattered. So for instance, what this means is if you have a still lake, you can see your image in the water. You can see a reflection in the water. But if there was rain falling on that same lake, you won't be able to see your reflection anymore. Okay? So because light is diffuse. Okay. So here's the property. A beam of light is reflected. This angle is called the angle of incidence. This angle is called the angle of reflection. these two angles are equal to each other. Okay, so that's how light reflects. Retroreflection is the following. See, if you shine a beam of light on a mirror like this, you see if you shine a beam of light, it reflects such that the reflected beam is going parallel back. Okay. Now for this guy, so if you have, if that corner was a mirror, you can shine a light like that. So if these two were mirrors, this beam would go there and come hit right back. But if I shine it like at an angle, it will go over there. So if I want that light beam to come right back at me, what I want is a corner like that. Now, if I hit this beam anywhere, that beam will come right back at me. That's called retroreflection. Okay. So if you have three perpendicular mirrors, this beam will come right back at you. All right, so this sphere, transparent sphere, acts as a retroreflector as well. Okay, this beam goes in there like that and comes right back. Okay, now you might ask, what is the use of this? See these signs, how do you see these signs at night? There's no light in them, so how do you see those signs? So what is happening is the paint in these signs have little retroreflectors, and light from your headlight is hitting them and coming right back at you. Okay, so these guys use retroreflection. These little things in your taillights, if somebody's driving ahead of you and they don't have their lights on, your headlight will hit those little corners and come right back at you. Okay, those little plastic retroreflectors. Here's a retroreflector on the moon. So when we went to the moon, we placed these retroreflectors, and we do this, we shine lasers and hit the retroreflector, and that beam comes right back at us. And from the time delay, we can measure the distance to the moon up to a few inches, 2-3 inches. All right. So like I said, light travels at different speeds in different media. So here is the speed of light in vacuum, and this is the speed of light in a medium. In any medium, light travels slower than in vacuum. So the refractive index is greater than 1 for all media. Okay. And the slower light travels in that medium, the greater the refractive index. And so here is a refractive index for various glasses. So if you get glasses, the highest refractive index you can buy is about 1.67, and that's the most expensive glasses that you can buy. Okay. Again, refraction is the bending of light when it travels from one medium to another. If it's traveling slower in medium 2, it bends towards the normal, and if it's traveling faster in medium 2, it'll bend away from the normal. All light paths are reversible. So if it travels in this direction, you shoot a beam like that, it'll go back exactly along the same path. Okay. So all paths are reversible. Mr. Snell tells us how much exactly the light will bend. Okay. If n is the refractive index of medium 1 and n2 is the refractive index of medium 2, n times sine theta 1, this is called the angle of incidence, this is called the angle of refraction. Okay, so this formula tells us exactly how much light will bend when it goes from medium 1 to medium 2. Okay? This is known as Snell's law. Okay. All right, so we are going to use the bending of light to make things like lenses. Okay, so if you make a lens like this using glass, okay, you shine a beam of parallel beams, it'll get focused here. Okay, so This is called a convex lens, or also, it's also called a converging lens. Okay? And for obvious reasons, because it's converging a beam of rays. Okay. This is called the focal length. The distance from the center of the lens to this point is called the focal length. Now, for all lenses, you have two focal lengths, two focal points, one on the right and one on the left. And the focal lengths for all lenses are the same. Okay, both the focal lengths are the same. The strength of a lens is 1 over the focal length. Okay. So smaller the focal length, stronger the lens. Okay. And when this focal length is measured in meters, the strength is in diopters. That's what the optometrist does. Okay, so for instance, my glasses for distance vision are 5 diopters. So that means the focal length for the lens is 0.2 meters. 1 over 0.2 is 5. Do you know your strength? Okay. Do you know the strength of your glasses? Hello? Do you know the strength of your glasses?
It's like
1.25. Okay, so a little over 1, so the focal length is a little less than 1 meter. Okay, so that's what that means. By the way, so for distance vision, you use what is called diverging lens. The focal length is negative, so our power is minus -5 versus -1.25. Yours look around -2, something like that. Yeah. This is a concave lens or a diverging lens. This is what we use. This is what we use for distant vision. Okay, so let me show you what's going on here. Okay, so like I said, my power is actually it's about -4. So -4 means the focal length is minus 0.25 meters. 1 over 0.25 meters is 4. Okay? That means I can't see beyond 25 centimeters. Okay, so what is this guy doing for me? My eyes can't see beyond this point. So if I have to see my friend here, what this has to do is it has to form an image of him beyond my far point, within my far point. And now my eye can take over. Okay, so anything I see, the image is being formed within this far point. Okay, so that's what's happening. This is the far point for this lens, the focal length. And no matter where I place the object, the image is formed within the focal point. That's how distant vision works. Okay, so that's how these lenses correct distant vision. Okay. All right, so when you wear a contact, this is the shape. So the contact is sitting on your eye like that. Okay. Did you guys understand? All right. All right, so this is a diverging lens. And if you shine a beam of light, it diverges these light beams. And these light beams, if you were looking at these light beams, they appear to come from this focal point. Okay, and that's the focal length. All right, so here's a converging lens, and what it's doing is it's forming an image here. Okay, this is the focal point. Here's the object beyond the focal point. Okay. Now, to form an image, what you need to do is start at least 3 rays preferably from a point on the object. And these are called principal rays. We'll tell you the properties of these. Okay, so this is the principal axis. The principal axis goes through the center of the lens. Okay, so ray parallel to the principal axis will pass through the focal point. A ray going through the center of the lens goes through undeflected. A ray going through this focal point will emerge parallel to the principal axis. So you just need to know the properties of these three rays to construct images. When rays actually meet at the image point, this is called a real image. Okay, let's look at this guy. So here's the object, and so here's a converging lens. This ray that would have gone through this focal point emerges parallel to the principal axis. This ray going through the center goes undeflected. This ray going through the parallel to the principal axis would go through that focal point. Now, if you were looking at these rays, what is your brain hardwired to think? Your brain is hardwired to think that rays travel in a straight line. So you would think that these rays are coming from that point. And that's where the image is formed. And since rays are not actually meeting there, this is called a virtual image. So this is what happens. Have you guys used a magnifying glass? Magnifying lens? Okay, so you have small print, you use a magnifying lens, and the object has to be placed within the focal point, and you see a magnified image. Okay, so this is a magnifying glass. This is how a magnifying glass works. All right, so for image formation, you need to know properties of three rays. These are called the principal rays, again. A ray parallel to the axis will go through the focal point. A ray going through the center of the lens goes undeflected. This ray going through this focal point emerges parallel to the principal axis. Okay. This is a concave lens. You have a question? I'm going too fast?
That one went pretty fast.
Okay, let's go back. No, okay. It's you're here. You paid money for it. All right, so you know what is the principal axis? It's a line that goes through the center of the lens, and it's perpendicular to the lens. Okay, it's just an imaginary line. A ray parallel to this axis will go through the focal point. A ray going through the center of the lens that's the only ray that'll be undeflected. Okay, so a ray going through the center of the lens will be undeflected. A ray going through this focal point will emerge parallel to the principal axis. So now you know the behavior of three rays, and you can use that to construct any image. You know? Here's for a diverging lens, a ray parallel to the principal axis will appear to come from this focal point. So it diverges, but it'll appear to come from this focal point. Here's this ray going through the center of the lens will go undeflected. Okay. And okay, so here is a converging lens acting like a magnifier. If the object is within the focal point, then this lens will make an enlarged image. Okay. So what does a microscope do? What does a microscope do? It magnifies. So a microscope essentially is using two of these lenses to magnify twice. Okay. All right, so here's a mirror. Here's a plane mirror. Here's a concave mirror. Here's a convex mirror. This is the kind of mirror that they have on supermarket aisles. This is the kind of mirror that is in the side view mirror in your cars is a convex mirror. This is a mirror that you have in your bathroom when you want to magnify something. You know, you want to magnify a shaving mirror, okay, or a makeup mirror. And this is a virtual enlarged image. Your side view in your car always makes a smaller image, an upright image. And you see it's in your mirror, side view mirrors, they'll always tell you that it's hard to judge the distance of the object from looking at the image in your side view mirror. For a plane mirror, the image distance is exactly equal to the object distance. Okay, so in a plane mirror, if somebody is standing 4 feet in front of the mirror, the image is 4 feet behind the mirror. Okay, so if you so this is how you make rooms look bigger. If you have this room, you make this a plane mirror. The image of that wall is, this is 10, let's say this is 20 feet, the image of that wall would be 20 feet behind there. So now this room will look like 40 feet, feel like 40 feet. Okay. All right. Here's a concave mirror. Okay. They use mirrors like this, parabolic mirrors like that, to make telescopes. So if this were starlight, that's where this image of the star would be formed. Okay. The focal length for a spherical mirror, the focal length is half the radius of the sphere. Okay. So there's the center of the sphere and there's the focal point. It's half the radius of the sphere. All right, so this is showing you a concave mirror. There's the object, there's the image. Okay, this beam is reflected like that. A beam going through the center goes straight back, and that's where the image is formed. Okay, the reds are the image. When the rays actually meet at that image point, these are called real images, and these are virtual images. To see these images, you have to project them on a screen. See these images, you just look at these beams of light and you see the image behind the mirror. Okay? This is a real image, that's a virtual image. Here's a convex mirror. This is the side view mirror in your car. There's the object and there's the image. That's a virtual image. Okay? Convex mirrors always make upright images, and the images are always smaller than the object. All right, this is an important relationship that you need to be aware of. Okay, P is the object distance. So let's say here's the object, and I'm just going to, so here's the image, object. This distance is P, and this distance is Q. So it's relating object distance, image distance, and the focal length of the lens. And this formula works for mirrors and lenses. Okay, so it works for both convex, for all these 4 devices. The same formula works. Okay? And so this is important in figuring out where the image will be formed. Yeah. Again, I'm going to mention this, but you don't have to worry about all of this. So it turns out that the focal length can be positive or negative. Okay, so for convex lenses, the focal length is positive, and for concave lenses, the focal length is negative. And the rule is, if the focal point is on the opposite side of the outgoing rays, then that's focal length is negative. If the focal point is on the same side as the outgoing rays, then focal length is positive. Okay, so for these guys, the focal point is on the same side as outgoing rays, the focal length is positive. So again, the focal length is negative for this guy, focal length is positive for this guy. Okay. And so that's why your power is -2 diopters or -1 diopter or whatever. Okay, we are using this kind of lens. Q is positive if the image is on the same side as the outgoing rays. Okay. So Q, the image distance will be positive if the outgoing rays are on the same side as the image. So for instance, in this case, here are the outgoing rays and the image is on the opposite side. Q is negative. Again, you don't have to worry about all of that because we won't be using that in problems. Okay, this is something you have to understand. Magnification, which you all know, is the image height divided by the object height. Image height divided by object height. So next time you use a microscope in the lab, you guys use microscopes that have 50 magnification, 50 times magnification, 200 times magnification. That means the image is 200 times larger than the object. Okay? That's what that means. Now, so a microscope has two, the microscopes you guys use in biology labs. Do you guys know what the magnification of those things are? Do you guys remember? It's probably around 200. Again. So they all use multiple lenses. Okay, so here's what's happening. This is the objective lens. This is the eyepiece for a microscope. There's the slide, little thing on the slide, and it's placed beyond the focal point, and it forms an image here. And that image is within the focal point of the eyepiece, and the eyepiece acts like a magnifier, and it makes a virtual image there. Large virtual image. Okay. So that's how multiple lens instruments will work. Okay. You form an image from the first lens. This image will be the object for the second lens, and here is the final image. Okay. So generally, this first lens will form a magnified image, a larger image, and then again you're magnifying this second image as well. So the overall magnification is the product of magnification of the individual lenses. So generally the eyepiece magnifies a little, and then the objective magnifies a little, and then the eyepiece will magnify even more. Yeah. So that's how compound microscopes work. So the simplest compound microscope is constructed from two thin convex lenses. Again, the first lens is called the objective, and the second lens, the eyepiece. Okay. The image produced by the objective, this is the objective lens, the image produced by the objective becomes the object for the eyepiece. This becomes the object for the eyepiece. When you combine two thin lenses, okay, the focal length of the combined lens is 1 over f1 plus f1 over f2. Okay, so this is important. For instance, in your eye, the cornea does 75% of the work. Your lens does only 25% of the work. But they're close enough where you can combine their focal length. Okay, and the effective strength of your cornea and your eye is the effective strength of the total effective strength is the strength of the cornea plus the strength of your lens. Yeah. Okay, so here's how contact lenses will work. Okay, so this curvature matches the curvature of your eye, of your cornea, and then, okay, so they'll shape this flat. So this lens can be thought of as this lens plus that lens. Okay, so you can draw a thing like that. Okay, so you see this lens is a combination of this lens plus that lens, this plus that. Okay, and if you're doing a distance vision correction in your contact lenses, this has to be more powerful than that, and then you can have distance vision correction. Okay. So do you guys know how doctors see the inside of your body using an endoscope? Yeah. So they can insert tubes in your esophagus, and you can see the inside of your, for ulcers and stuff like that. Here's how that thing works. Okay, now you start a beam of light from glass and go into air. Okay, if you shine this beam at an angle greater than a critical angle, this is totally reflected. 100% of that energy is reflected. Okay, so for instance, if you make a glass fiber, these are called optical fibers, you shine a beam of light, and 100% of this light is reflected. This is what makes cheap internet possible, fiber optic cables. You can pack a lot of information in there on a light beam. Okay? And send that information across distances. Okay, so 100% of this light is reflected. Okay, so that's what's happening here. See, this is a plastic tube, and that's that letter there you can see over there. See, it's 100% of that light comes through, and that's what's happening. So this could be inside your stomach, and you can see the ulcer or whatever it is that you're trying to see. Okay, so you're using total internal reflection or fiber optic cables to do that. Okay. All right, guys, so that ends that. So you got a little flavor for geometric optics, and we'll use some of this when we talk about vision next week, which will be the last lecture. Okay.